So process capability. Lean Six Sigma uses the data, right? It uses data to make sure the process is consistently is going to meet the customer, specification. Okay, so we have a process and then customer specification. Whether your process is going to meet that specification or not. Sometimes your process is good, but it's not aligned with the customer, right? So that is a problem. So by looking at the data, then engineer quantify whether process is capable. It's capable to improve or maintain the quality standard. What is the process capability? That means whether your process is going to consistently produce output. The output can be different. It can be products, real life product. Sometimes it can be service. So whether your process is going to meet those specific requirement that was set by the customer or designer or another section. Okay, what is in the process capability? We have two definitions. The specification limits. The specification limit is going to be what the customer expect for a product or service. Okay, how can we obtain those specification limits? We can remember we have voice of customer VOC survey. These are some of the ways to find the specification limit depending on the product service. And so that is coming from customer, right? Customer tells you these are my specification limit. But then you have a process. The process you have to look at the process itself. See, based on those tools we used, last week, XBAR, R chart. That those chart tells you where your process is, right? Whether your process is in control or out of control. So this part is gonna tell you how your process is, right? The situation. Sometimes your process might be in control. You remember those, fluctuation? We had the upper limit, lower limit. So your process is, perfect. It's making, part or service, which are all, within those, upper and lower control. But it does not meet that, customer need. It's not within the specification limit. So that is a problem, right? We have to see, how can we improve the process in order to meet both control limits, the process is in control, also the process meet the customer requirements. So if we plot those, upper limit, the specification limit and control limit, we're gonna have something like this. And we have different, abbreviation for each one. Lower control and no upper control. This is where we had that chart. Remember, this is time. UCL, upper control limit, LCL, and this is control limit. So we now have these two terms right here. So that was, vertical, now this is horizontal. Okay? And then you get a survey from, you ask your customer what is your specification, what are the size of this part, it should be. For example, you're producing, a gear, very good example for mechanical engineering. Always when we say mechanical engineering, that gear is the symbol for mechanical engineering, right? So the diameter of that gear has to be within this size, plus minus 10, let's say 1 inch plus minus 5,000 of an inch, okay? So 1 plus 5,000 of an inch is gonna be the upper specification limit. And 1 minus 5,000 of an inch is gonna be the lower specification limit. So this and this are not related, is it? These two. This is control, the process. Your process is capable to make, let's say, 0.1 inch plus minus 5,000 of an inch. The process is in control, but it's outside just range. Make sense? So it satisfies first part, whether it is control or out of control, but it does not satisfy the second part. So I have a couple of examples here. Based on this description, can you tell me this means control limit, process control limit, or a specification limit defined by customer? So dimension accuracy in 3D printing, we have a tolerance specifying that. Oops, it was showing the result. Specifying the printed part must have dimension within 0.1 millimeter of the CAD model. So is it process control limit or a specification limit defined by customer? So your part must have this dimension. So this is something that the customer is asking, right? This is not related to process. Make sense? Is that clear? So what is the answer? Answer is a specification limit. So you have to decide, you have to find out whether this is a specification limit or process control. The next one. We have a manufacturing process control export chart. Export chart, this one. So it's going up, sometimes it goes down. Average diameter of bolt should range from these values as indicated by historical data analysis. What does it say? Is it a specification limit or process control? So this, you have two limits, right? 9.95 and 10.05. These two numbers, are they control limit or control limit? Everyone agree? Yeah, it's coming from the export chart. So it is, control limit. How about this one? We have a chemical composition of a steel, right? Requirement for the carbon content must be between 0.2 carbon, 0.2%, and 0.3 for a specific grade. So is it, a specification or control? How many say specification? Raise hand. How many control? So you see the requirement. This is saying requirement that carbon content must be in this range. And this is not coming from this chart. It's coming from engineer, metallurgists. They say the carbon content must be this much. And this 0.2 up to 0.3 is a high carbon amount. If you want to have the regular steel in the construction we use, it's about 0.02%. Very little amount. This is a high carbon steel. It's too much. Medium toward the high carbon. So when you have high carbon steel, it's a little difficult to work with, especially in welding process. Okay, so this is a specification limit. How about this one? The quality control, it says variation in coating thickness should stay within 2 and 4 microns based on the daily measurement of the sample. They measure sample every day, and they say if your those sample have to be in this range, 2 and 5 microns. So make sure you understand this. Like sometimes the problem you have to based on the information you have to see what is that one, whether it is a control limit or a specification limit. These are a good example. Variation in coating thickness should stay within 2 and 4 micron. Control limit or a specification. It's coming from chart. When it's coming from this chart, that is control limit. It's related to process, not customer. So control limit. Okay, how about this one? Service delivery. Moving range. Control limit indicate that moving average percentage of the late delivery should not exceed 5% over time, based on weekly data. Remember, they have some data and they found this information from the data. So this is another way to find this belongs to which category, right? So the moving range helps monitor trends in the delivery performance, ensuring consistency in meeting customer expectation. Okay. Control or a specification. If your process is gonna be in control, it should stay, it should not exceed 5%. So this is control limits. Okay. Last one. Response time for customer support. So you define it that custom. It didn't show up here. Response for customer service. You define it that customer, anyone that asks a question, they have to receive an answer within 24 hours, right? So is it a control or a specification? So they have to get the answer. If they don't, it's not meeting the requirement. There was one video, here, it was interesting.
process capability is the ability of a process to meet customer specifications, to meet their CTQs, without additional efforts. So the question is, how good is it as of today? Where are we right now? So here's just a quick question, a fun question. So who requires more effort to win the World Cup? So whoever requires more effort is going to be less capable. For this example, Elon Musk, he's not a soccer player, so he's going to be less capable of winning the World Cup. Ronaldo, we'd say, would be more capable at this point in time. Here's another way of thinking about it. Can Apple make a laptop as thin and as durable as the customer expects without additional effort? Or is there more investment needed to get there? And can they do those things consistently with minimal variation? What is their capability of doing that today? Now here's another example. So what about process capability for producing weather-tolerant O-rings? So O-rings are used for insulation, and on the Space Shuttle Challenger, one of the reasons for the explosion was these O-rings. They weren't weather-tolerant. They didn't respond well in cold temperatures. As we assess our capability of producing weather-tolerant O-rings, one measure we might use is ring flexibility in cold temperatures. Now, when we calculate capability, we can look at the capability of ourselves, so we can ask, can we meet our customers' expectations? And we can also look at the capability of our suppliers. So who can provide us what we need?
Okay, so the idea is to measure, to quantify process capability, right? We have those specification limit defined by customer, and then we have a process. It has upper control and lower control. Based on those information, we can define whether our process is capable or not. Okay. So let's say this is upper specification limit, right? Defined by customer, and lower specification limit. And this is your process. Process has this upper control limit and lower control limit. And these are, as you see, and this is the center. And this is not in the center, right? And it's called off center. So that is gonna reduce the process capability. Another problem is that you have a large variation. The process, the center of the process, is right in the center of these two numbers, but it has a lot of variation. You may have some part outside these range. Okay, so that is not also good. So process variability is too large. There is no relationship between control limit and specification limit. And how can we calculate, the process capability? So we have a ratio. That the ratio is defined as a USL minus LSL. You have to calculate, this R, the difference, right? This difference goes to numerator, the top of the top of this division, and 6 sigma is the process. The process has a standard deviation. You multiply it by 6, so that is going to be this portion, right? This is upper portion, this is the lower portion. Okay, when is it that number is going to be 1? When this ratio, this length, and this length will be the same. when, you know, Six Sigma and this, you know, portion exactly the same, then that will give you a number 1. CP is gonna be 1. So that's our, you know, objective, to define, to make this ratio as 1. So this, you know, ratio on the top and this ratio on the bottom. But that is not sufficient. You know, we're gonna look at it later why it's not sufficient. You know, just looking at, you know, the CP. For example, when you look at this diagram, this length and this length, they are almost, you know, the same, right? And that gives you number 1. That is the first, you know, requirement. Number 1. That is, you know, we want to have number 1. But we are getting some parts that are outside this, you know, this range. So we are producing some part that the customer does not want them, right? The process is in control. You don't have any problem, but the, you know, customer does not require them, does not want them. So that means, you know, only looking at CP is not going to be sufficient. We have to look at another term. Okay. Before we get into that, the next term, sometime you may want to, you know, find sigma. The sigma you can calculate using this equation, R bar divided by D2, right? We talked about it last week. And you can use a standard deviation divided by C4. This number can be calculated, you know, can be determined from the table. At the end of the, you know, textbook, there is one chart based on the sample size. If you have, you know, 5 sample, this C4 and D2 are going to be different, right? So the problems, you know, provide, you know, the sample size, and then you go and find those factors from the chart. And then you can use, you know, this equation to find, you know, CP. Average sample, standard deviation, and average range. So acceptable, you know, CP is, you know, plus is should be 1 or more. What does it mean, you know, if we have, you know, CP more than 1? If CP is more than 1, it's, you know, let's go back to that chart. Means this one is wider than this ratio. Make sense? This is 6S, and this is, you know, the upper part. If this one becomes, you know, larger, and you divide it by this, so your CP is going to be larger than 1. Make sense? Right? Look at this one. We have, you know, CP bigger than 1, right? Let me use this one. Let's look at the first one. So this is the lower specification limit, and this one is upper specification limit. And the 3 sigma is here, 3 sigma deviation from the average is right there, right? So your CP is going to be, you know, because this is the upper part of the division, this is the lower part, so this one is going to be bigger than this, so you get, you know, a CP bigger than 1. Make sense? Let's go here. So both of them, both lengths are the same, so you get, you know, CP1. And then here, CP is getting a smaller. Why? Because this is the process, you know, 3 sigma here. This is the ratio that is going to be in the denominator, and upper and lower specification limit, which is on the top part or upper part of the division, is a smaller. So CP is smaller than 1. Sometimes you may say, I'm gonna make my CP bigger than 1, right? So that is the idea. You wanna make it 1 or bigger than 1. So this is something like that. Or this one or this one. But what happens between here and here? In the price-wise, the cost-wise. This means your process is in control and it's very tight. You're making some part that has very tight tolerance, right? So that tight tolerance is gonna cost you, right? So you don't want to spend too much time to make the process in a way that, let's say, you make you pay extra cost for that process. The best is gonna be something like this. So you don't have additional cost. This is gonna be one cost saving. I'm gonna this one. Upper LCL. You're making gear again. The gear has 10 inch plus minus 5,000 mm. So both of them, for this one will be 9.95. This will be 10.05. Okay. So both of them, LCL, and LSL, they are on this side, 9.95 inch. Now I'm gonna make LCL small, with a smaller type. Let's say I'm making it, by process in a way that produces. This is center, this is gonna be 9. This one will be again 10.5. Now here is my UCL, which is 10.0. This is gonna be 9. So now I'm, in this process, I was using a machine that is gonna be, let's say, $10,000, 10K. And this one, because I'm producing a part which it has a tighter tolerance, then I have to use, 20,000. I invested in a machine with this much, then I was able to, make this, part with a tighter tolerance. So you have to see whether it's gonna worth it, right? Because it's so tight, but you paid more. The initial cost, investment is more in this sample. So you have to, it's better to go, with this one, because if you wanna make it tighter, you have to invest more. So that is the main takeaway. If you wanna make the process, smaller than upper specification limit and lower specification limit, it's gonna cost you. And whether it's worth it, right? Any question? Okay. So you see, all these processes, they have sigma standard deviation 2, right? For all of them. The process is in control. As you see, the shape does not change. Shape is going to be the same, but you know the average is changing. In the top, case, the average was 50, right? It was right in the center of USL and LSL. But when you calculate the CP, what was it? This length divided by this length, right? That is 2. How about this one? This one divided by this. Again, that is 2. We repeat it, this portion divided by this portion. Again, that's 2, right? What's happening? CP is not going to be enough because it does not show you where that process is. It's going off center, right? It's not in the center. It's not within that specific lower and upper specification limit defined by customer. It's going outside. The process in control, it's making the part that was needed, right? That was intended in the process, but it is not, satisfying the customer requirement, right? So then we have to find another factor. We have to use another factor. So this shows, that the length is getting smaller. So we have to use, a term that can define, deviation from the upper limit or lower limit, because you see, this is getting smaller. That one was bigger. So that brings us to another, factor. Where is this? This one, yes. You have upper control, upper specification limit minus average of your sample divided by 3 sigma, and this is for the lower specification. Okay, this is for upper specification. So the shape I showed you in the previous one was for upper specification, and this is for lower one. So we have to calculate this one. If this one is getting smaller, what does it mean? It means your process is getting to that the upper specification limit. If your part in the CPL is getting smaller, means your process is getting to the lower specification limit. And the factor is CPK. CPK will look at both of them, and then it tells you you have to pick the minimum of those two. Which one is the lowest? The lowest value of those CPL or CPU will be your factor CPK. So acceptable CPK should be 1. When is CPK 1? CPK 1 will be when your this portion divided by this portion is the same. It's going to be those two lengths will be the same. That will give you CPK 1. So if your CPK is lower than CP, that means your process is off center. When is it that you get negative number? Look at this one. USL minus U divided by 3 sigma. When your average, let me draw it here. So this is when we have UCL, LSL, USL. This is, you see, USL minus average, right? Divide by 3 sigma. This one and this one, they are exactly the same number. This portion gives you 0, right? So you will have 0 CPK. But if you move this one further this way, I'm gonna draw, bring this USL here, right? Your mu is larger, right? USL is smaller. This is, let's say, 5, this is minus 10. When this center is gonna exceed USL, so you see the result will be minus 5, right? So in that case, you get a negative number. Again, that is out of your process capability is low. Sometimes they ask you whether your process is 3 sigma capable or 6 sigma capable. If 6 sigma capable, it's gonna be tighter like this one. It's 3 sigma, like it's gonna be like this, a larger variation. And each one has a criteria. For example, this one, 6 sigma capability means CP has to be larger than 2. This one. This portion divided by this portion has to be 2. And CPK has to be 1.5. And 3 sigma capability means CP is going to be more than 1, CPK has to be more than 0.65. Okay. For what are the application? For 6 sigma high reliability industry like aerospace, they use 6 sigma. 3 sigma, very tolerable in less critical application. General manufacturing industry, they use 4 sigma. Based on those equations, there are a couple with summary. You can review them later on. For example, when CP has a value of 1 or greater, the process is producing products capable of meeting the specification limits. When your process is in the center, the CP and CPK are the same. If the CPK is negative, it means the center of your process is completely outside the lower and upper specification limits. The number 9. So here is one example. We have a hospital that is using X chart, X bar chart, and R chart to report the time it takes to process patient account information. This is a service industry. The sample of 5 application. Sample of 5 application means what? N, the lowercase n is 5. It's taken each day. Every day they have 5 samples. The first 4 weeks, 20 days, they found X double bar 16 and R bar 7 minutes. If the R bar, no, the upper and lower specification limit is 21 minutes and 13 minutes. So this is the definition that was provided by the hospital. They wanted to make it 21 and 13 minutes between those two. We need to find Six Sigma, CP, and CPK. Okay? For Six Sigma, for CP, we need to know Six Sigma, right? We can use either this one based on the information provided, and then use that sigma to find CP. Okay? And then we have to calculate these two. The lower one of these two, you see, minimum of this one will be our CPK. So should I use sigma, R bar divided by D2 or S bar divided by C4?
R bar divided by D2.
Yes, because we have R bar is given. Yeah. Sigma is R bar divided by D2. So if we look at, so how many samples? We have 5 samples. We go to this chart, right? And 5 is D2, 2.326. Go back here, and R bar is 7 minutes. If we divide that one, we will get 7 divided by 2.326, almost 3. Okay, we have this part. Now we can calculate CP. CP 6 times 3, and USLs is 20 minutes minus 13 minutes. 8. Divided by 18. So if you want to plot it, look here. 16, right? And then 16 is 5 difference. This is 21. Now, what is this one? This is LSL, right? This is USL. This is mu or X double bar. And then what is the standard deviation? The standard deviation is somewhere here. 3 sigma. It will be like this one. Yeah, I have a plot showing that one. What is CPK? CPK, let's use CPU, USL, this one, 21 minus 16, correct? What else? 3 sigma, 3 times 3, so that is 5 divide by 9. And CPL, the lower one, is 16 minus 13. 3 times 3, 9. So my CPL is smaller. CPK will be 1 over 3 or 0.33. So it's completely, it's not capable. The process is not capable. Also, the process is not, centered. So when we plot it, we will have something like this. You see, this is the upper specification limit. This is the lower specification limit, and this is where my process is, right? Yeah, maybe I put the wrong number. This is not correct. These values are correct, but this, I put the wrong, chart here. Okay. Yeah, while you are working on this class activity, I will work on this one. Discard. Any question?